at the Lawrence Berkeley National Laboratory. After his undergraduate education in Germany, he obtained his PhD from the University of Toronto and was a postdoctoral researcher at UC San Diego and the California Institute of Technology. He has been at Berkeley since 2005. His research is on the precision calculations of the standard model predictions, and more recently, on the ways we can use quantum computing to solve difficult computational problems in particle physics. He's developed quantum algorithms for parton showers to understand processes in collider experiments, and has devised several methods for mitigating gate and rebound errors. So, without further ado, please welcome Christian Bauer.
Thanks very much. So just so I get an idea, how many people are there? Are most people at home? Are some people in the school, or is it just you two in the school, everybody else at home? I'm just trying to get a feeling for at home. Most people at home. Good. So let me, yes, I have to share my screen. That's probably the first thing I need to do. Otherwise I can't do that. Very good. You guys can see this, I assume, right? Works? Okay, everybody can see my screen, right? I'm not hearing anything for some reason. Do you guys hear me? Okay, good, very good. Okay, so yes, so it's really great to be back here. It would have been fun to do it in person. Maybe we can do it at some point in the future. But yeah, so as you heard, I want to tell you a little bit. So I've talked in the past about sort of my work on particle physics, the standard model, and calculations there. And today I want to tell you some things about quantum computing. I will probably spend most of my time just talking in general about quantum computing, and then only sort of at the end give you one small example of some of the work we have been doing. If you guys want, you can ask some questions after, and I'm happy to tell you more about the work I have been doing, or my group has been doing. But I thought it makes sense to spend some time on sort of telling you a little bit about the more general, what is quantum computing? Why do we think it's interesting? And so on. So let's just get started. And, so this is interesting. This is well before my time as well, but this is how computers at some point looked, right? This is sort of a really old computer, I think from the 50s or 60s. And probably that computer is way less powerful than anything we have in our iPhones today. And then, of course, things really progressed with time, right? At some point we had sort of, some first Apple computers. This was a breakthrough when the Apple I came out, which is, the first sort of personal computer with a mouse and an operating system and so on. This is sort of, I think, when I started, laptops sort of did look like that. But nowadays we have, this is how our computers look like. And if you want to do really scientifically challenging calculations, you tend to use computers that look like this, supercomputers, where essentially each one of these racks, let me actually get my annotate and my laser pointer, which doesn't, where is it? Sorry. Why do I not see can you see my mouse pointer actually? Or no? I don't know why I cannot see sorry. I don't know why I can't get the laser pointer to work. Well, anyways, yes, anyway, so each one of those things in each of these big cupboards is like essentially one computer. Okay, and you can see there is hundreds of thousands of these computers all wired together. And so really what has happened over these years is that computers have just become more and more powerful. And essentially computing power, you probably all know, right? Computers are made out of transistors. They're just some simple gates that control sort of, and it's sort of binary numbers that you can combine. In the end, it's all sort of some AND gate, OR gates, and so on. And these can all be constructed from transistors. And really the computing revolution has happened because we can fit more and more and more transistors onto chips. And this is sort of a law that was sort of proposed by Moore back in, I think, around 1970, when only the first few of these points were available. And he essentially said that the number of transistors we can put on a microchip roughly doubles every 2 years. And what they really thought at the time is that this could continue for maybe 10 years or something. But what is remarkable, so what you see here in this plot is on the x-axis is the years, right, from 1970 to 2020. And then you see the transistor count on the y-axis, and that is in a logarithmic scale. So you see back in 1970, we had about 1,000 transistors on, 1,000 to 5,000 transistors on a microchip. And now we're sitting at that number that's like 50 billion chips on a transistor. And so far, this law has it doesn't look like it's slowing down. So that is really, really remarkable. And that has really been what's driving a lot of the quantum revolution the computing revolution, why computers get better and better and better. Now, so let me look at that again on here's my version of that same plot. So again, on the y-axis, you have computing power. On the x-axis, you have the year. On the y-axis, you have the computing power, which is essentially the number of transistors on the chip. And it's some linear scale if I make the y-axis exponential. And so what is interesting is, so there is a similar law we can ask about quantum computers. So quantum computers, and I'll talk a little bit more about this, is essentially you have instead of having a bit, so a computer is driven by bits, and a bit can be either 0 or 1. You can think of that as true or false, but I can write numbers in binary representation all through these zeros and ones. Now, what is different about a quantum computer, it doesn't have bits, it has what is known as a quantum bit. So it's also a bit that can have two states, 0 and 1. But the difference to a classical computer is either 0 or it is 1, and a quantum computer can be both 0 and 1 at the same time. And I can sort of change how much 0 and how much 1 a quantum bit is. And as we'll talk about, I can use that to get more computing power. Now, what is important, and I will talk about this a little bit more, is that the computing power is exponential in the number of bits that you can put. So on a classical computer, if you have more transistors, you can have more bits. And essentially, it's a 1-to-1. For every transistor you roughly add like 1 bit if you want. And the computing power is linear in that. So if you double the number of transistors, you double your computing power. What is important on a quantum computer, if you double the number of qubits, you quadruple the, much more. If you add 1 more qubit to your system, you double the computing power. So for every qubit you add to your system, you double the number of states you can store. And so that means, and there is, if you look at sort of the development of quantum computers over the last 5 to 10 years, there's actually several companies working on this, IBM, Google, even other companies, lots of companies are working on this. And they've roughly doubled the number of qubits that you can put on a chip every 3 or 4 years. So that means I'm again having sort of a law where roughly the number of qubits doubles every fixed time interval, but then the computing power is exponential in the number of qubits. So that means if I were to plot that quantum Moore's law, which is sometimes called quantum Rose's law, then the computing power looks something like this. Now, this is sort of using a version that was developed back, I think, 10 years ago. Things are a little bit slower. It's actually not quite wrong, right? So if you remember, in about a year ago, Google announced what they call quantum supremacy. So quantum supremacy is essentially, so what Google claimed, and it's mostly true, that they have discovered one calculation where a quantum computer outperformed a classical computer, and one of the best classical computers that there is. And so, it's not so crazy that sort of in around 2020, these lines cross. Now, it's not quite right for almost every application. This is a calculation that was tailor-made to be solved by a quantum computer. So, you know, it's not such that from now on quantum computers will outperform classical computers. So maybe a more realistic version of this, you know, maybe in order 20 years or so, we might get to a point where quantum computers outperform classical computers. But it is really important that that really steep rise is just what all the hype of quantum computers. When you hear so much about quantum computing in the press and in the news, it's because of this, because at some point it's just such a faster increase with time than classical computers. And so one of the questions you might ask yourself, you know, is you read a lot of this in the news. As you know, not everything you read in the news is true. So you might ask yourself, well, is it really true what is being said, you know, or is there, how much hype is there? And, you know, or is this all hype or is this truth, right? And so that is, you know, something I hope I can address a little bit in this talk. And, you know, it's somewhere in between there. It's not true that any calculation you can now do in a classical computer, you will instantly do better on a quantum computer. But let's dive a little bit into this. By the way, I should, oops, I don't know what happened. Oh yeah, so this is good. If you have any questions, I will try to keep an eye on the chat. If you have questions, put them in. I'll try to answer them as they come. And if they're kind of longish, I might defer them to the end. Okay, so the first thing is quantum computers rely on quantum mechanics. That's sort of the first, you know, the first important thing. So let me maybe ask, can you guys just give me thumbs up if you have a rough idea of quantum mechanics? Just so I get an idea. Okay, good. That's what I assumed. So I see a couple of thumbs, but not too many. Good. That's what I was expecting. So I'll give you a little bit of information of what quantum mechanics is. So quantum mechanics is a really fascinating topic. You typically learn it in as an undergraduate if you do a physics, if you go into physics in college, and it's an amazing thing because it's totally counterintuitive. Everything you think you know about how science works and how physics works, quantum mechanics seems to go against your intuition. That's why it's really fascinating. And so let me give you an example. So let's come up with a very simple example. You might have heard of this. It's called the double slit experiment, but let's walk through this. So imagine, so what I have here, I have some screen on the back, okay? And I have sort of a solid wall in here that has two holes in it. So it's sort of a solid wall with like two holes in it or two slits that you can have. And what I'm going to do is I am going to shoot particles from the left onto that wall. And, you know, I can do this with electrons. I can do this with other particles. And so if you think about this for a second, what you would probably assume will happen, well, you know, if an electron hits the wall, it will bounce back. Okay, it doesn't make it through, but any electron that hits one of these holes will just go through and hit the screen at the back. Okay, so your expectation is probably that when you shoot a lot of electrons, you see a lot of hits. Half of the electrons will hit somewhere over here behind this hole. The other half of the electrons will hit over here behind this hole, right? That is a totally sensible way to think about this from anything that you've probably learned in high school about physics. That is your expectation. So let's actually look at what happens. So here's an experiment. So what I'm now doing is let me look at what happens on the screen. Okay, and so what we're doing is we're looking at in time. So here we've only had about 10 electrons go through. So 10 electrons have made it through and hit the screen. Okay, and so here's where these electrons have hit. Okay, so my two slits would be roughly here and here. Okay, well, let's keep going. Let's throw 3 more electrons at it. This is what it looks like. It's kind of interesting, right? It kind of looks random. They hit kind of everywhere. And I certainly don't see a concentration here and a concentration here very much. Well, let's keep going. Let's actually see what happens. So maybe now something is developing, right? If you squint a little bit, you maybe can see a pattern. Let's shoot a few more electrons. This is what happens. And so what is really fascinating, you actually do see regions where it kind of does look like I have slits, right? There's sort of more electrons here and less electrons over here. But then I have again more here, less here, more here. So it's certainly not two regions where the electrons hit and the other regions are dark. It seems to kind of have sort of alternating bright spots and dark spots.
Mr. Bauer,
Yes?
would it be possible for you to turn on the pointer? Because it's a little difficult to see the mouse.
I could figure out how my damn pointer, let me stop my sharing for a second and try that again, okay? And I do not, there's something about my Zoom that is not too happy. Let me try it again. Share my screen. Okay. Let me try. Wow, my Zoom is like, I don't know what's going on. It's like super duper slow. Let's see this. Let me hit annotate. I don't know why my mouse pointer doesn't come up. It's really, oh, because I know why, because I put a laser, I put, what is it? More? Why can I not? I can draw on it. Right? I should be able to click the annotate and then select if I remember right. It doesn't work. More, does that work? Well, I'll draw on my screens and then we'll do it that way. Yeah, so what you see, I can't, sorry. Yeah, actually here you see it even better, right? So now you sort of see you have a bright spot over here, like bright region here, dark regions over here, another bright region over here, and so on. So we alternate bright and dark regions. But it doesn't look like that I have sort of these two slits that I had. So can't go forward. Wow, this is ridiculous. How do I not know how to use Zoom anymore? Let me quit because also my computer is sort of, give me 1 second. Let me close some windows and see if that makes a difference. Some of my computer is getting really hot. I should probably have a quantum computer to give this presentation. I'll say, wow, I can't do, let me stop my screen sharing one more time. Sorry, guys. What is going on here? Let me close a couple of windows and see if that makes a difference. Sorry, close, let's close anyway. Sorry, guys, almost there. So why? Can I try upstairs? You know, let me share my desktop, see if that makes it easier. Okay, so now I see my whole screen. Annotate. Why can I not? Does anybody remember? Am I doing this wrong? If I click on, oh, here, now I got it. Annotate. No. I'm supposed, do you guys remember? Am I supposed to click and annotate? And then I should get a laser pointer, right? Okay, I just, for the life of me, I can't figure it out. Okay.
I think if you click view options on the top, then you're able to annotate.
I don't see any view options, unfortunately. Where is it here?
Like where it says you are screen sharing, then right next to it, there's a little arrow.
Oh, that one? No. Oh, the arrow here. Move. Let's just move to bottom. Okay. Well, I'll
Or it's in like the little bar where your mute and video thing are.
No, that's my settings. I am totally perplexed. Participants chat. I was convinced it was here. Okay. Well, maybe I can make my laser pointer bigger, my mouse pointer bigger. Hold on, give me 1 second. References. See, now I'm on annotate and I can't stop it. Well, sorry, system preferences, mouse pointer. Sorry, this is ridiculous. I've given so many Zoom talks in my life. And mouse, track point, is it here? No. Mouse, give me 1 second, and then if it doesn't work, we'll Okay, well, I'll try to use annotate. We'll make it work. Okay, let me, yeah. So essentially, so what is happening? Can you see the mouse pointer here on the white screen? You can see it, right? Reasonably well. Okay, so yeah. So what's happening? You shoot these electrons in, and somehow what we're seeing is we sort of see, these electrons hitting sort of in these stripes. So there's some stripes where the electrons hit, some stripes where they do not hit. And so how can we understand this? And so let's actually look at a similar system that sort of, again, has sort of two of these holes where actually we would expect something like this. Because imagine I send a wave. So this could be a water wave. You can try to do this experiment in your bathtub if you want. So you send a wave onto that slit. Then essentially what happens at each of those holes, these waves turn into circular waves that they kind of go out like this. And you get essentially where you sort of have these, so you have peaks and troughs of these waves, and where sort of the two peaks come together, the wave amplifies, and you get sort of an overall bigger wave. And where peaks and troughs meet, like here, right? There's a peak here and there's a trough in the other wave, you sort of get cancellation. And so if you had waves, you would actually expect some pattern like this. But now you can say, well, but we're not having waves, we're shooting particles, we're shooting like electrons, or you can also do this with like gold atoms, you get the same effect. And so the only explanation for what we're seeing is that actually the particles are actually like waves. And so that is what the magic of quantum mechanics is, that essentially instead of having definite particles, you actually have waves of objects. And everything you kind of know about waves, namely a wave, right, can be in multiple points at the same time, right? A wave kind of just spreads out. So you have one electron, but it really is a wave, which means that electron can exist at multiple different points. So if you think this through, the reason we can have this interference, because this one wave that's coming through here is going through this slit and this slit at the same time, and then those two waves interfere. That is actually what's happening in quantum mechanics. That electron will go through both of these slits at the same time, because really an electron is like a wave. It can go through two things at the same time. And that is the thing that is incredibly counterintuitive. But it is really what the rules of quantum mechanics really tell you. A state can be in what is called a superposition. So that means it can be of distinct states. So it can be distinct states all at the same time. And that these states can interfere with one another. So if you have sort of two states, the two troughs of a wave can amplify to make another wave. What is interesting, I didn't talk about this, but if you actually, it's totally fascinating, if you actually build any detector in this experiment that tries to see which of these holes does my electron go through. So imagine you put a camera here or something that detects if the electron goes through here or through here, that entire interference pattern will collapse and you actually get that result. That result. So as soon as you measure where something goes through, you will get a result that looks like this. Okay, so what happens in quantum mechanics, that as soon as you do a measurement, that wave, or that what is called a wave function in quantum mechanics, and it's called, it collapses and leaving only one of these possible states. And there's one other important thing about this is namely so we have an amplitude. So what we call as an amplitude is like, so if I have two states, I can say it is an amplitude to be in this state or in this state. And the probability with which, when I do a measurement, I find a state in one of these many possible states is the square of that amplitude. So the reason I'm telling you all of this is because that is what is really important in quantum computing. So now I told you I have a qubit. So you can think of this, you have some quantum state that can be in two different states at the same time. It could be some atom, for example, that can be in a ground state and an excited state. But because of quantum mechanics, it can be both in the ground state and the excited state at the same time. And what we've learned over the years is how to actually control that very well. So I can actually control how much of a ground state or how much of a state like this is in these two states. So I have a tight control that I can do and move things. I can say I want to move something that is purely in the ground state and maybe 50% of the ground state and 50% the excited state. So we can have actually control these quantum systems, and therefore we can build a computer. So every qubit is now this thing that can be in one of two states at the same time. But when I do a measurement, I'm collapsing this, and then I find the qubit to be either a 0 or a 1. Okay, so let's have a little bit more look at this. And yes, so wave interference patterns, that's exactly right, what was said a little while ago. So let's try to understand how we can use this. So let's try to do a very simple problem. You know, we can all write this. I wrote this in Python. So imagine I have a function. It's one of the most simplest function you can think about. It takes an input x and returns an output y, which is just x plus 1. Okay. So I have this function. Every time I call this function with a value x, I get as a return x plus 1. So that means here's my classical computer. And so if I feed that classical computer my input x equals 1, the classical computer will spit out y equals 2. If I want to know the result for x equals 2, well, I need to run that function again. It will tell me that the result is 3. So that's great. So for every time I want a result, I need to call this function. So now I just told you that in a quantum system, I can engineer something that it can live in a superposition of many different states. So it can not just be one state, but it can be many states at the same time. So imagine I could create a state X that is the state 1 and 2 and 3 all the way up to the integer n, and all at the same time. And I give it an amplitude. I say the amplitude of being in the state 1 is alpha 1. The amplitude of being in the state 2 is alpha 2. It's just some numbers. And just believe me for a second that I could engineer a state like this. So we can control quantum mechanics enough that I could engineer a state like this. If I run this through my quantum computer, if I call my quantum computer this function on that state, it will actually create, it will add 1 to all of these numbers. So it will give me back y equals alpha 1, so the same amplitude, but it will turn the 1 into 2. By the way, this funny notation that I'm using here is how we represent a state usually in quantum mechanics. Okay, so what is fascinating about this, I did a single calculation, right? I called this function once, this quantum function, a single time, but I've actually got the results of n additions out, right? I now have in the state, I've stored the result of 1 plus 1 is 2, 2 plus 1 is 3, and all the way up to n plus 1. N plus 1 is n plus 1, okay? However, and so you might say, wow, that's amazing, right? I've done with one function call, I did n calculations all at the same time. And you might say that that's a quantum advantage right there. Well, you have to be a little bit careful, because I told you, as soon as you measure anything, as soon as I look at what that quantum state actually is, all that quantumness disappears and I'm getting one number out at the end, okay? And that means I might get the result y equals k with a probability alpha k minus 1 squared. So after I've actually looked at my output, I've only gotten a single number out. And it's worse, right? I don't even know what that is the answer to. Okay, so I've not actually gotten any information out of that calculation right now. And so really what you're learning from this is that after measurement, so in this example, I've only learned the result of a single calculation. And I've not actually achieved anything, right? This has not helped me do anything and do anything better. All the results that we had in memory, if you want, quote unquote, they've all been lost through a measurement. And so really the difficult part of using quantum computers is to design algorithms that use this quantum parallelism. The fact that this quantum computer did all these things at once, that you can use that information. And essentially if you think about this problem a little bit more, what you learn is you need to use some collective property of that quantum state. So if you just look at sort of the output of one thing, that won't teach you something. You need to use some collective property. And so maybe I'll pause for a second here. These funny things are like vectors. You can think of them as vectors. More generally, they're states in what is called the Hilbert space. But yes, you can think of them as vectors. So maybe quickly see if there's any questions. Otherwise, I'll give you one example of a quantum algorithm that actually where you can sort of see what is known as a quantum advantage, where you can sort of beat a classical algorithm. So let me maybe actually do that. So the example here that I have in mind is, imagine you have a lot of files. You know, imagine somewhere in your office, there's all the files of every single student in the school. But the problem is that somebody was not really smart. They didn't order the files alphabetical. They just dumped all the files randomly into these cabinets. And so now a student comes and says, I'd really like to get my transcript. And now here comes the poor person who's running the archive. He says, uh-oh, this is not alphabetical. Now I have to find your file. And what is he going to do? Well, he's going to look at each file one by one until they find your file, right? So you can write this as an algorithm. He just literally goes over all possible files. So for file and files, he checks if it's the right file, if the file is the right one, so it has the name of the student, then I grab the file. How long do you think? Maybe type it into the chat. How long do you think on average? How many queries, how many files does the person need to pull out until they find the right file on average? What do you guys think? Oh, it says it on the slides. Very good. Yes, but Alejandro got the right answer. N over 2. Very good. Yes, I was thinking of taking that out. Good. It is on the slide. Yes. So the algorithm will take about N over 2, right? Because it's roughly after half the files, you have a 50% chance of having found the right file. So that's what it takes roughly. So it scales what we call linear with N. So if you have twice as many files, it takes you twice as long to find the right file. So let's try to see if we can do this better on a quantum computer. And so I have to introduce something here. So let me, and again, you have to just believe me that we can do this. I will create a so-called quantum state. So I have a database of all the files in the system. So each one of those lines that you see here is one of these files. So I have a total of N of these lines. And let's imagine for a second that red one is the right one. But of course, I don't know that yet, right? I don't know anything about this yet. But if we pull out the red file, I will get the answer, yes, it's the right file. If I pull out any one of the other ones, the algorithm will tell me, no, it's the wrong file. So now what I will do is I will create a state that has equal amplitude for all of the files in the system. So I put my system in a superposition of all files with equal amplitude. The problem is if I now were to randomly choose one of those files, right, I will get each file with the same probability because the probability is equal to the amplitude squared. And so the height of these lines is my amplitude. So if I now randomly measure the state, I will get one of these files with random probability, which is of course classically what we would do if you just pull out a random file. But here's something we can actually do on these quantum systems. So this is something I can train a computer to do and is possible to do with quantum resources. So I can say, because remember, I can act on all things at the same time. So I can actually tell my computer, act on all the states at the same time, and the states that is the right file, flip the sign of the amplitude. Okay, I've not actually accomplished anything because all of them still have the right magnitude. Remember, I told you the probability is the square, is the square of the amplitude. So this probability is still the same as this. I've not done anything yet. But what you can now do, so in this yellow line, I'm telling you what is the average amplitude. That is also something you can compute. Now, of course, if all of them are the same amplitude, the average amplitude is just the value of all of them. Now, if I flip the sign of one of them, the average amplitude goes a little bit down, right? Because now this guy contributes negative to the average. Now here's another operation I can do in my quantum computer that is called invert about the mean. So I'm saying is flip every amplitude, its value around the mean. So that means I'm taking an amplitude, say this one that I'm having here with my cursor, and it's a little bit above the mean. So the new amplitude is a little bit below the mean. However, this amplitude, that value down here, is a lot below the mean, right? Because it's negative, and it will go above the mean. So that turns this state into that state. And what you can immediately see, if I now were to measure this state, remember the probability of finding this file is the square of the height of that bar, which is now a lot bigger than these guys. So the probability of now actually finding the right file is bigger than the wrong file. But I can actually do this algorithm again. So start the state that I just had, now do the same thing again. Invert around the mean. That now again drops the average. Invert everything around the average. And now I've grown this again. Okay, I can keep doing this algorithm until at some point, the average, this line will be so big that once I invert it, the average will go negative. And then then that algorithm won't continue to improve. But I can continue this algorithm until the average is negative. And the important thing is that keeps increasing the amplitude of the correct file. That means if I measure now that amplitude, and you can prove that the probability now, if you measure it, that you get the right file is very large. Okay, and now you can calculate how many iterations of this algorithm do I need to do until that amplitude becomes negative, or that mean becomes negative. And it takes you, the number of iterations goes like the square root of the number of files in the system. Okay, and so that means if I have 4 times as many files in my system, I only need calculate twice as long, whereas the classical algorithm needs to calculate 4 times as long. So that's a pretty significant improvement. Imagine I have 1,000,000 times more files. The classical algorithm needs to calculate 1,000,000 times longer. The classical computer only takes square root of 1,000,000, which is 1,000 times longer. So that's a factor of 1,000 improvement, right? That's really important. Now, what is really important here, remember, I sort of did these tricks, invert around the mean. I use the collective property. The mean is a collective property of that state, okay? And so this is known as Grover's search algorithm. And it gives you an improvement of a linear scaling with the system size to a square root size. There's other algorithms. The reason I didn't, probably an algorithm you've heard about is Shor's algorithm. Shor's algorithm is something, so it's actually, so I don't know if you guys know this. So one really hard problem computationally is how to factor numbers. So you probably remember, right, if I have the number 15, I can say 15 is 3 times 5. So the question is finding the prime numbers that you need to multiply together to get any number. So any number you can write as products of prime numbers. And it's essentially, there's no good classical algorithm. If I give you a really large number, there's no good algorithm to find all the prime numbers that you have to multiply together to make that number. And that problem is what is called exponentially hard. That means if I make the number just twice as big, so that the problem really scales like 2 to the sort of number, if you want the number of digits in my system. So if I have a 10-digit number, it takes me, say, 1,000 operations. An 11-digit number takes me double as long. And so the more digits you add, the problem quickly becomes totally intractable. Now you might say, why is it so interesting to factor numbers? You know, it's interesting mathematically, but what is really important that every security scheme that we use nowadays, any kind of, you know, if you go on your wireless network and it's encoded with some password, all of that stuff, the reason we can encode communication relies on the fact that it's incredibly difficult to factor large numbers. So if you had a computer that could factor numbers really fast, you could break any encryption algorithm that essentially exists nowadays. So that's why that is a really important problem. And Shor has proven about 20 or so years ago that a quantum computer can factor large numbers exponentially faster. So essentially, so at the moment, we don't have quantum computers that could do this. They're not powerful enough. But you can imagine why, government agencies are really nervous about these things appearing. And that's sort of also why there's a lot of funding recently in this. It's a lot of that is driven, I think, by the fear that, the Russians or the Chinese could actually develop a quantum computer faster than us, and they could break all of our encryption and sort of read all communications that we have. And so that is really one algorithm. It's the reason I didn't put it here, because it's a little bit difficult to explain how that algorithm works. But anyway, so that's an interesting algorithm. You can Google it. You can try to read up on yourself how Shor's algorithm works. But that is sort of one of these algorithms that's really driven a lot of the of the mainstream, of the media attention to this. Now, it's not something that is really worrisome, because at the same time where we're developing quantum computers that so I think by the time quantum computers can break or can factor large numbers, quantum mechanics will also be the way we actually encrypt our communication, and that can't be broken. Okay, so it's not something that we really have to worry about. We just have to make sure that we develop new encryption schemes, and there's many techniques that are known that you cannot break. And so towards the end now, I want to tell you a little bit about that. Then that goes towards my own work, and which I'm personally am most interested in. I think probably the most important application of quantum computers is to solve problems that actually involve quantum mechanics. And as I'll try to convince you, most of these problems that actually have quantum mechanics in, and those are sort of the kinds of problems that I talked to you the last time I was here, are essentially, many of these problems are completely impossible to solve from first principles on a classical computer. And so many of the techniques of the things I talked to you the last time was sort of finding clever ways to do computations, but they're never the exact computation. We just don't know how to do these calculations exact. And what is interesting, as I'll tell you, is that quantum computers have the potential to actually do that. No, the short answer is I have not, and I also have a question what that is. But if Ryan, if you can maybe afterwards, you can ask that question again. If it's a serious question, given the smiley, I'm not 100% sure. So let me tell you, and let me start from a quote. Maybe some of you have heard of Richard Feynman, who was sort of one of the giants in particle physics. From the 50s sort of to the 90s. And he is actually the person who sort of for the first time really thought about quantum computers. And here's a quote that he gave at a conference at MIT in the early 80s. And so they were actually talking about quantum computers, and he was sort of saying, trying to find a computer simulation of physics seems to need to be an excellent program to follow out. So they were talking about what are important calculations to do on a quantum computer. And then he said the real use of a quantum computer would have to do with quantum mechanics, because nature isn't classical. And then he went on to say, and if you want to make a simulation of nature, you better make it quantum mechanical. And by jolly, it's a wonderful problem because it doesn't look so easy. So Feynman was all about solving really hard problems, and he did solve a lot of really hard problems. And so this was really his idea, that we should really use quantum computers to solve the important quantum mechanics or quantum field theory problems that we have in nature. And so let me try to tell you, I sort of had that plot earlier, right? On my chart is Moore's law. And this is again the years. This is again computing power, but I've increased my scale a lot higher. Okay, so I think previously my thing ended at somewhere like 10 to the 10 or 10 to the 11. I now went up to 10 to the 200. And now that classical computer line lives all the way down here. So you might ask, well, why did I make my scale so high? You can't really, see things. Well, your science teacher will tell you should always pick the scales that you can actually see the plot. Well, the reason is because the physics problems we are trying to solve that have that you need quantum field theory and quantum mechanics live up here. We kind of need that kind of computing power to solve the problems that we care about in a lot of areas of science, like, for example, what I'm doing in particle physics. So that seems a problem, right? I mean, look at that line, look up here. So one way we could say, okay, we're trying to solve this problem. Let's wait until classical computers have caught up. So I can extend my X scale as well and see, well, how long do I have to wait? And it's great. In the year 3200, our computers might have caught up to where we need to be. So we can say, okay, let's all go hibernate for 1,000 years, and hopefully our descendants will in 1,000 years still know what we cared about now. But that is kind of impractical. Like, no scientist wants to work if they know we can only solve a problem 1,000 years later. But if I draw that quantum computer line, that's what it looks like. Okay, so that's what exponential growth will do for you. And we probably all learned a lot about exponential growth during COVID, right? there's a very big difference between a positive, if something grows exponentially, it looks really small at the beginning, and at some point it just takes off and goes totally out of control. And in COVID, that's a really bad thing. For quantum computer, it's a really good thing. And so, let's actually look at what that means. That means, by sort of 2050, we could hit these goals. And, I much rather wait for 30 years to solve a problem than to wait for 1,000 years, right? So that is really what we're talking about. And this is why I think Feynman said why probably the most important application of quantum computers is that. So let me tell you a little bit. Yes, the answer is yes, it is exponential, because remember what I told you is that it's really super exponential, because, so the reason here is, I'll answer that question right now, because the number of qubits grows exponentially with time, but then the computing power is exponential in the number of qubits. So it's really doubly exponential, and that's why it is exponential. It is, well, with the system size, so exponential is not faster than factorial, but I think double exponential is faster than factorial. So yeah, it's an incredibly fast growth that you get. And so, last time I was here, I told you that we're trying to understand, sorry, there's a question from Leo. Maybe I'll just take a hand raised and take that question right now. Leo, did you want to ask a question? If you do,
sorry, no, that was a misclick. Sorry about that.
Okay, no problem. Yeah, so last time I told you about the standard model, that we sort of have, quarks up here, these 6 different types of quarks. We have leptons. We have these matter particles, like a photon for the electromagnetic interaction, gluons for the strong interaction, W and Z bosons for the weak interaction. Then that we have that Higgs particle that was discovered now almost 10 years ago, or almost exactly 10 years ago at the LHC. And that we're trying to understand, how well that standard model works. And I also told you that we have sort of dark matter in the universe that the standard model cannot explain, and that we're using big particle accelerators like the ATLAS or the Large Hadron Collider in Switzerland. So just to orient yourself again, just to see, I showed this before. This is a schematic. So underground, 100 meters underground, we have this particle accelerator. Just for scale, right? This is the airport of Geneva right here. This is the border actually of France and Switzerland. So Switzerland over here, France over here. And then you have these different experiments. And the way this looks underground is something like this. This is the tunnel underground. This is the accelerator. And you can see there's this like curvature. So this thing is 27 kilometers in circumference. And so we're using all of this. And the question we're trying to answer at the end of the day is everything we see at these experiments in agreement with the standard model, for which we have some equations that we can write down. And if we find something that does not agree with the standard model, well, then we found physics beyond the standard model. And then maybe we can then investigate whether that physics that we found could be responsible and explain dark matter, for example. But what it really means is I need to be able to go from the theory over here to experiment over here. And that is something, even if we use the most powerful computer that we have, this is a computer that is at Lawrence Berkeley National Lab where I work, we just can't do it. And that is sort of this thing that I told you, if we wanted to wait on the advancements of those kinds of computers, we have to wait for about 1,000 years. And so the point is, if we have these quantum computers, and that is a picture of a quantum computer, and we can talk why they look so crazily complicated. But the answer is that at least we believe we can do, if we have the right size quantum computer, we can do that. And so what I want to do the last few minutes here, I just want to tell you, give you a little intuition of why that is. So what we are trying to compute is something like this. So remember at these Large Hadron Collider, we have two protons that we're colliding. So we have some state with, I'll answer that one at the end. We'll go through the questions again. So we start with sort of some initial state. So we start with some protons at some time, let me put it at time minus t. And I want to measure a state, let me call it x, that has all these different particles. That is essentially what I see in my detector. And the question is, how does a state evolve from some time minus t to that final state in time t? What is the probability that my two protons will evolve in a certain final state? And that's really what the LHC measures. And in quantum mechanics, you can write this through sort of some object, which is called an evolution operator. And you can write down what that is. We have all the equations to write this down. And so you could say, well, let me just compute this object. Well, the problem is, remember somebody asked earlier if these things are vectors, and I said, well, they're states in a Hilbert space. Well, the problem is in quantum field theory, the states are infinite dimensional. So these are infinite dimensional vectors. And the reason is because essentially you can think of this, we have a proton, and the proton can exist at every different point in space, right, if you want. And so there's infinitely many points in space I can have. And essentially all these different particles that I get in my final state, they can be at infinitely many different points. So that is essentially what happens. So we have both the position at where particles can be is infinite dimensional. And then you have to remember in quantum mechanics, everything is waves. And essentially the amplitude of those waves is again, a continuous. It can be an infinite number of values. And so that is what makes that incredibly complicated to compute. Now, if I could go onto a system where these things are not infinite dimensional, but finite dimensional, right? Then I really have vectors, and then this is like a matrix, and I can actually just do the computation through matrix multiplication. Well, how could I do that? Well, I just told you one of the complications is that my space is infinite dimensional, right? It's continuous. Well, I could just say, well, let me not sample my space everywhere. So imagine I want to sample the position on the slide. Well, I could just give you the exact X and Y coordinate on that slide, and I tell you where I am on the slide. But you can also imagine, well, let me only give you discrete points. So, I say, I only have these black dots that I can tell you. And if I want to characterize a point over here, well, then I approximate it with a point that actually sits right here on that black dot. There's a few numbers here that you might want to have is what is the distance between 2 points and what is the overall size. We call this a lattice. But the important thing is there now is a finite number of points I have. And I can do something similar. I can now say essentially my field values, let me what I call digitize this. So instead of having a continuous set of values, I only allow a discrete set of values. Actually, every computer does that, right? We have 32-bit or 64-bit bit computers, and that actually means they can't represent all possible rational numbers. They can actually only represent a discrete set of numbers. So if you're taking a programming course, you've learned that. These points, Anushka, are sort of points where I sample so essentially I'm saying is I'm not allowing to look at every possible point on this sheet on my slide, but only at discrete individual points. And so the idea is if I at some point take the distance between these points to 0, then I'm going to again sample and L to infinity, then I'm sampling every possible point. So it's an approximation to the problem. But if I essentially double the size number of my points, I get better and better precision, right? If I can make that a better and better approach to the right answer. So you can now try to work out how big is my vector. And you find that the size of my vector has the following. Size is the number of values I use for my fields at every lattice point raised to the power of the number of lattice points. Okay. So now I have this, everything here is vectors. This is a matrix, and I can just do matrix multiplication. So great, I can tell my computer, my laptop to do matrix multiplication, right? So the next question you have to ask, well, how big are those vectors? And so there's one other thing you need to know. Remember, I told you everything is waves. And one important thing that I didn't tell you yet about quantum mechanics is the more energetic or the more massive an object is, the shorter that wavelength becomes. So the wave becomes more and more squished together. And so you can imagine that if I have a lattice with a particular spacing between 2 points, the smallest wavelength I can possibly see is of the size of this. Imagine I put a wave in here that oscillates 20 times between these 2 points. Well, I can't tell that it oscillates 20 times or 10 times or 3 times because I just don't have the resolution. Okay, so the shortest wavelength I can see is roughly the distance between 2 lattice points. And that's why, of course, I want to at some point make this lattice point smaller, the distance smaller and smaller. And the largest wavelength I can see is the size of my lattice, right? If I have something that is a really long wavelength, I can't resolve that on a lattice here. And so that means, because energy is given by 1 over the wavelength, that essentially tells me, yes, so the waves, you can think of as sine waves, but the point is if you have a sine wave that oscillates really, really, really fast, and I only allow you to sample this at discrete intervals, you can at some point not resolve that it actually oscillates, right? In order to see that a sine wave goes up and down, I need to sample it a few times between the point where it goes up and down. Does that make sense? And so if I don't have the resolution to sample my sine wave between where it goes up and down, I cannot actually see, I cannot count how many times it went up or down. Does that make sense? Okay. And so that means by this argument I just gave you that the smallest energy I can give is given by 1 over the size of my lattice. The largest energy I can resolve, I can describe with a lattice that I had is 1 over the distance of the lattice. So now you can say, imagine I want to, sorry, this is not the full range of the LHC. Imagine I want to describe a particle physics problem that has an energy range of 3 orders of magnitude. Doesn't really matter what these scales are, but this is like MEV to GeV, there's 3 as a factor of 1,000 in between these energies. If you look at this formula, that means you need 1,000 lattice points and in each dimension. So that is 1 billion lattice points in total. And so now we can say, let me just, because I'm running a little bit out of time, let's say I have 32 states at each lattice point. So that means the dimension of my Hilbert space, or the size of my vector, is 32 raised to the power of 10 to the 9. So, you know, you've probably all learned that infinity is larger than any possible numbers. So you know that that is not true. 32 raised to the power of 10 to the 9 is an actual number, so it's not infinity. But you know, it's an unimaginably huge number. This is not 32 times 10 to the 9. It's 32 to the power of 10 to the 9. That's unimaginably huge. And that's why a classical computer could never, ever, ever do this calculation. Now, on a quantum computer, remember I told you things are logarithmic and quantum computers exponentially better. So that means the number of qubits that I need is only logarithmic in that. So it's a number that's 10 to the 9. That's still pretty big. It's 1 billion qubits. That's a lot of qubits. We have about 100 now. But that is something I believe is possible. If we keep doubling the number of qubits, we will get there. Sort of by 2050, 2060 or something like this, okay? And so this is why we believe quantum computers can solve problems like this. And you can show that you can actually implement this matrix multiplication with reasonable resources that are possible to do on future computers. So this is sort of the main idea of one of the ideas of how we can use quantum computers to solve problems that we essentially can really solve problems that are so big that are impossible to do on classical computers, but we can do them on quantum computers. And that's where really a lot of the research is about. I'm just going to show, I'm not even going to explain really what this plot is, but just so we can do something. So what we did, this is now a real physics problem. We try to compute some object that matters in physics, in particle physics. I won't have the time to explain it, but what I just want to show you here is in yellow is some analytical calculation, and the points in black are actually results we got by running this simulation on a quantum computer that IBM has built. And we were able to actually get the results. You know, we could make a quantum computer actually get the results that we wanted to get out. So, so there's many other fields in science that can use quantum computers to solve problems. Chemistry is a huge area where we believe, so in understanding really how molecules work and what excited and ground states of molecules are, is something that is incredibly hard to do with classical computers, and quantum computers really have the potential of doing these kinds of calculations, you know, exponentially faster. I mean, for you, exponentially faster really means you can do them, whereas you cannot do them on a classical computer. That's what I really mean by, let's say, exponentially faster. And there's many other industries that can use that, from the car industries to the airline industries. They're full of problems they're incapable to solve using classical computers. And so here's just a couple of, you know, which I kind of found interesting, all sorts of quotes from the news that come from all sorts of different industries, from aerospace, automotive, you know, engineering, and so on. So it's really a fascinating field that is growing incredibly fast at the moment. I just want to end now and go to some questions. So this is sort of all the people that have worked with me, all the way from professors at the university all the way to undergraduate students that we have worked with. And I'll leave it here. I'll have questions, and I know that there's already some questions here. Maybe I can start going through those, but please also unmute yourself and just ask questions or raise your hand, however you wanna do it. So let me quickly go through. Here was the first one. What R&D, that was Oliver. What R&D factors or research groups are likely to influence the value of the exponent? So I think this question is really twofold. It requires us to build the computer. So it's a hardware development. So it really means we need to be able to scale up the computers. These computers right now, they have a lot of noise. So you think you do a certain operation to your computer, and you actually make a little mistake, and then these mistakes build up over time. So there's a lot of R&D that has to happen just on the experimental side, like building these machines. But then is also algorithmically, how can we build algorithms that really use these computers? Oliver, let me know if that answered your question or did not answer your question. You can do it in chat or by raising your hand. Maybe let's go to, if we have questions that are coming from people real, let me take those. Suhita, I probably misspelled that name, mispronounced that name.
No, that's correct, sorry. So you mentioned that physicists were able to use the quantum systems at IBM to simulate a real physics problem.
Yes.
So I'm curious, can you tell us a little bit more about that?
Yes, so I will actually put a link into chat, and I can send it to Anushka, or, you know, and you guys can send it on. These machines, so there's actually, so are you asking how you would run on a quantum computer, or what we did to develop things? What was the actual question?
So like, what is the physics problem, and how did you use the quantum computer?
Yes. So the physics problem here was, so, you know, as I said, I could not explain it in detail, but essentially what you can show. So let me give a couple of minutes of introduction. So really what I sort of lied here. So if you actually try to do the full energy range of the Large Hadron Collider, you actually need to go in almost, you know, another order or 2 orders of magnitude higher in the energy range. So that means you actually need 10 to the 14, 15 qubits to do a calculation that you might actually care about. That is probably more qubits than we might have even in any of our lifetimes. So what we started to think are there other calculations that are not as complicated as literally simulating the entire Large Hadron Collider. And so essentially we kind of showed that there are, that you can sort of build up a prediction for the Large Hadron Collider out of individual pieces. And one of those pieces is a particular matrix element that is sort of that I've written here. And it's very hard to explain what that is. It essentially describes to you if you have a really fast particle moving through sort of, vacuum, what is the probability sort of exciting gluons in that? And that sort of will tell you what other particles you will see in your detector. And so it's essentially, so that is one of these objects from which you can build up an observable that you see at the Large Hadron Collider. But this is an object that is, again, is impossible to compute classically. So you could never use a classical computer to directly compute this object. And so what we've tried to do here and showed in a very simplified object that you can actually build an algorithm that would be able to compute this object on a quantum computer. And in a very small size, we were able to do this computation. Now, about how we did the computation, what is actually really cool, IBM, you can Google IBM Quantum, and it's actually like a cloud computing. You can literally write your own, everybody can do this. You create an account on IBM Quantum, and you can submit your own quantum computing jobs, and they will run on an IBM quantum computer. So all of you can do this. Now, admittedly, we have access to slightly newer machines and so on than the public has, but IBM will make available to the general public quantum computers to actually run some simple algorithm. And if you dive into it, you program these things using Python. So you could actually run sort of this Grover's algorithm that I showed you here, and you could actually run that on a quantum computer. And probably you guys could do that. You need to work a little bit and understand how things work, but it's not that complicated. Let me see, what were, and that was Oliver's question. Then the next question, what is the field 5x? Yeah, so the way you should think of this, remember I told you we have, at the beginning, I told you we have an electron, and really in quantum mechanics, every particle is like a wave. We sometimes call this wave particle duality, and that is really that weird thing about quantum mechanics. But essentially what you think of as an object is actually a field, or is a wave, and a wave is essentially, it's an amplitude, right? If you think about what a wave is, it can exist everywhere in space. And in order to characterize a wave, you have to say, well, how high is the water at any given point? And if you tell me that, then you can plot how the water looks, right? And so essentially what a field is, it gives you an amplitude the amplitude or the height of something at every point in space. So what essentially this phi of x does, it sort of characterizes this wave function of an electron. I think I answered Anushka's questions about what the points represent. I hope I answered that question about the wavelength. And yes, Ryan, that's a really interesting question. So it is related to the Shannon-Nyquist thing. There's actually a big part of the Shannon-Nyquist. So to understand, so the Shannon-Nyquist theme actually doesn't have direct relevance on that sampling. Probably does actually, but where actually that Shannon-Nyquist theme is incredibly important. Remember, I told you somewhere here, I made the statement that's maybe sounded kind of crazy. I had this here. Let's do 5-bit digitization. You're used to using 32 or 64-bit digitization on computers. And essentially the Shannon-Nyquist theorem is a really good observation. It essentially tells you that with relatively low number of states, you can get a really good description. That is all coming back to the Shannon-Nyquist theorem. So Shannon-Nyquist theorem, for those of you who don't know it, is essentially saying that you can get an arbitrarily good representation of sort of a localized signal or a particular signal with only a finite number of points. That's essentially what the Shannon-Nyquist theorem says. So Anushka, your question, are the restrictions we have based on how small the distance between the points can be? Yes, in principle, yes, but I think the distances we try to do are well below So we can think of, well, no, actually, we really don't, because what these lattice points actually, so remember what the Heisenberg uncertainty principle says, is that I cannot put a certain particle at a fixed position. Well, really what it says, I cannot put a particle of a given momentum or velocity and specify the velocity and the position exactly. So that, for example, that means if I have a particle at rest, which means I know its velocity, its momentum precisely at 0, essentially that means the extent of that thing is infinite. It's infinity, right? I can't actually, I can't localize that object. And that is essentially, that goes back to this phi of x, right? I have every particle, if I put it at rest, has sort of a wave that I need to give it an extent. So what we're using this lattice for is just where we, where we sample. So imagine you try to characterize a wave. In principle, you have to tell me what is the amplitude of that wave at every possible location. But probably realistically, you're just going to give me a finite number of values of the amplitude of the height of that water, and then I can map that out. You give me a grid and you tell me the height, and that's good enough. And as long as you sample that finely enough that you sort of get the proper, you get the full trough and of the wave function, the peak and the trough of the wave, then that is good enough information. So that's really what that is. So it's not directly related to the Heisenberg uncertainty principle. Good. Leo's question, very good question. That is the $1 million question. So so the question, let me just read it quickly. How do you prevent decoherence amongst entangled qubits in a quantum computer? So first of all, what is decoherence? So decoherence means, I told you, we can put a state into a superposition of two states. And you probably remember, you've probably heard about Schrödinger's cat, right? So the whole idea that, this thought idea that you can devise a system where sort of a cat can now all of a sudden be dead and alive at the same time. And you can ask, well, why don't we see this in nature? Why don't we ever see a cat that is both dead and alive at the same time? And that is all coming back to decoherence. Essentially, any quantum mechanical system can interact with its environment. And essentially and therefore yes, it was proposed as a counter, right? That's right. It was proposed essentially as, this sounds really crazy, and therefore quantum mechanics has to be wrong. But what we understand nowadays, that essentially, if you have a system that is in contact with any kind of environment, it will, what is called decohere, and that means it will actually, these superpositions will disappear over time. And the larger my system is, the more it is entangled with the environment, and therefore the quicker that entanglement will disappear. So essentially a cat, you can prepare it into some entangled state, but it will almost instantly decohere, and therefore instantly collapse into either a dead or an alive cat. Okay, and so that's what decoherence is, essentially interactions with the environment. And that of course sounds really bad. So now I'm telling you that if a system interacts with the environment, it will lose that entanglement, or that fact that it can be in a superposition. The whole thing about quantum computers relies on the fact that things can be in a superposition. So now you can say, okay, let's work really hard to isolate my computer from the environment. And that actually explains that picture that I had at some point. Sorry, this picture. Sorry, one more. This picture. So what you see is actually not the quantum computer. What you see is called a dilution fridge. So essentially what you do is, in order to make a system not interact with the environment, you know that if you have a temperature is sort of, molecules moving around, right? And as soon as molecules moving around sort of at random velocities and so on, and as soon as if I put something in a system where lots of things move around all the time, these things will constantly bump into my system, and therefore it will interact with all the other stuff. So what you really need to do is you need to make sure that the environment doesn't jiggle all the time. So you need to lower the temperature a lot. And that's what these dilution refrigerators do. They can go to tiny fractions of a Kelvin and put your entire system into essentially absolute zero temperature, very, very close to that. So the short answer is, how do we prevent decoherence? Well, we try to isolate a system as much as we possibly can. put them in these fridges. But then actually, if you think a little bit about it, we want to program our computer, right? We want to act on our computer. I want to do something with my computer. If I want to interact with my computer, if I want to program my computer, well, I have to interact with it. I'm the environment, right? I'm not inside of that refrigerator. And so that means, by definition, a computer has to be coupled to the outside world. Otherwise, I can't use it. And that is really the hard part of all the building a quantum computer, that you need to make it as isolated as you possibly can, but still be able to control it. And that's really where all of that is happening. Is it because nature tries to achieve low? Well, it's so I'm not sure what the question is. If that's about the temperature, so that's just that essentially that is what temperature is. Temperature is literally things moving about. And therefore, if you want to stop things from moving about, you have to lower the temperature. I don't know if that was the question. Because essentially the way you can think of this is because the environment is something one way. So first you can just, well, you can, one way to think of it is that the environment system acts like an observer. So once it interacts with the environment, you know, the environment is something I can look at if you want. And therefore, sort of by construction, parts of that information has to disappear because I'm getting, by interacting with the environment, I can observe it. And therefore I can, I measure something, and I just told you that things collapse if I measure it. That's the best answer I can give. I can give a very technical answer, but that won't help. It will use a lot of math. Any other questions? Feel free to ask them in real time. We're real by raising your hand and unmuting yourself.
I meant about the fact that nature achieving low potential energy, about the decoherence when there's a lot of, when there are a bunch of states and everything's entangled with each other, that it naturally tries to resolve itself.
Yeah, I mean, you can, there is a, I think you're right. There's some relation to that. I think the precise statement is hard to make because it again, so, so you can essentially prove that through the interactions with the environment, and it's related to the fact that the environment is observable, is that, I think the easiest answer I can give is because the environment is observable, and therefore you start to put information into something that you can observe. Sorry, here's Ryan. Would it be accurate to say that when the system reacts to the environment, the superposition states changes? Yes, certainly. So absolutely. So once it interacts, so decoherence, you usually yes. So certainly it will mess things up. But it's more than messing it up. It actually really loses entanglement. So at some point, so I'm saying is, if imagine it were something, a system that just messes up the interference, but it still stays fully interfered, you could imagine I can actually counter that again, right? And try to correct these changes. So the point is, once things decohere, it's very difficult to correct that again. So that's why there's a little bit, so computers also make mistakes, but in principle, you can correct those again. So that's why I differentiated those two. Yeah, so I encourage you, there is quite a lot of, if you're interested in this, you can send me an email about it. Anushka has my email. And probably others too. Feel free to send me an email. I can point you to some, I think if you look at IBM Quantum, let me just see if I can find that very quickly. IBM Quantum KISS tutorial. There's some very simple, so it does require, at least you need to be, at least you have to accept quantum computing or quantum mechanics, right? So it won't teach you quantum mechanics directly, but if you, yeah, there you go. So if you go to this, they will actually teach you, and I think they will go through how to write things and probably teach you how to actually put it onto an actual quantum computer at IBM. So Qiskit is written by IBM. but it's just Python. So for all of you who know how to write Python code, you probably can write this. You know, it's in the end, you start a Jupyter notebook. And then start writing.
I had one question. How is it possible to do quantum computing without the computer being super cold? For example, like photonics.
It is. Everything, these computers are all incredibly cold. So that whole thing that you're seeing here, everything you see in that picture that I have right now on this screen is essentially all, there's one thing, there's like what is called dilution refrigerator, and you use all sorts of crazy amazing physics to cool something down. But yes, the computer sits at almost absolute zero. So it's not like, you know, my normal computer where I cool to get rid of really big like heat, but you really need to put this at absolute zero.
So it's not possible at all to have a quantum computer that's not super cold?
No, it's absolutely impossible. So the way you have this, so I think in the long run, I mean, so at the moment, the way, so you could not easily have a laptop, right? Because these dilution refrigerators, they're like a big, I mean, they're like a cupboard. They're big. There's enormous amount of wires that sort of go in and out. So it's a pretty complicated, no, of course, who knows? Maybe in 50 years, we've developed tiny dilution refrigerators. But I think, I mean, from this question that we just talked about, is just that if essentially things will decohere way too fast if you're sitting at room temperature. I think it's almost impossible. I suspect it will be impossible to do that if you're not sitting at almost exact zero.
I read once that you can use photons or something to like make room temperature quantum computers, like with quantum photonics or something like that. Is that like?
That's a good point. I don't know if you can, so I'm not sure about the room temperature part. Okay, maybe you're right. Maybe I'm actually wrong. So yes, so there's certainly, you know, any quantum, so any quantum system, any system, you can build a quantum computer of any system that has sort of quantum states that you can couple together and somehow can control, right? So, and so a lot of these things are actually done by superconducting circuits that can sort of circulate one way around, another way around. But yes, photons are quantum systems as well, and you can use those. There's lots of other techniques you can use. Yeah, so let me make the statement a little bit. So maybe I'm not sure actually now that my temperature thing. So I think the important thing is you need to isolate your system. Okay, it is important that you have a system that does not interact with something else. So, you know, in principle, you could imagine you go to total vacuum, right? And then it doesn't need to be, you know, at least that nothing bumps into it. Yes, so, and there are certainly photonic people trying to do photonic quantum computers. Using photons.
I just had a quick question.
Yeah.
Even if you did isolate it to a vacuum, would there be any problems with, you know, the quantum fluctuations of the vacuum messing with the quantumness of the qubits?
Yes, so you have to control all of those things. Yes, so it's not enough. Yes, so absolutely. So you could have a photon, now that can have vacuum fluctuations. So I don't know, you know, I'm not building these things, but yes. So the point is, the short answer is you need to make sure that you have a system that you can put in a certain quantum state and it will stay in that quantum state for a quote unquote long time. So I should mention, by the way, if we talk about long time nowadays, we're talking microseconds. Okay, so these computers, they stay coherent for, you know, a few microseconds. So at the moment we can run a computation, it has to finish in a few microseconds. But you know, that is improving all the time.
I think Ryan had a question in chat.
Oh, let's see. How is temperature affected in high gravity? You know, Ryan, now you asked me a question, I would have to think about it. Not sure how curvature affects temperature, just off the top of my head. Yeah, I'll have to take a rain check on that question. I'm not 100% sure. I don't want to say something that's wrong right now. So I'll just leave it at that. Any other question that maybe I can answer? I'll have to pass. Good. If not, as I said, feel free to reach out. Oh, one more question from Ryan. Yeah, so I will have to think about it. Ryan, if you send me an email, I can try to think about it some more. I'm just worried that by the time the weekend is gone, that I forgot the question. But if you send me an email, I'll think about it. Good. Well, it was fun as always.
Thank you so much for coming.
Yeah, this was awesome. I really, really enjoyed it. I know you have to go, so I'll let you go. But thank you so much for staying and answering all our questions. This was great.
You're welcome.
Thank
you
so
much, everyone, and enjoy being in person in the school. I'm sure.
Yeah, Ryan, I'll send out an email when I send out the recording.
Perfect. Great. Thanks a lot, everyone.
Bye. Thank you.
Bye-bye.
I stop recording.